One of the reasons that we learn about exponential functions, especially this exponential function with the base e, is because they're very popular in applications in physical sciences. So for example, exponential growth and decay is a process which obeys an exponential growth or decay function, which can be written with a base of e. So this is an exponential decay or exponential growth function. There are lots of values in here. So t is our independent variable. This is time. So that is where we plug in that this stuff has been decaying for a certain amount of time, or it's a bank account and interest has been accumulating for a certain amount of time. T represents the time gone by. K is the growth or decay rate. I'm just going to call it rate. It's generally a small number like 0.02 or negative 0.3 or something like that. It's a number, it's a tuning dial that dictates how fast or slow the decay or the growth is happening. This number right here is the initial amount of whatever it is that you're looking at. And over here we have the current amount. So I could tell you, hey, there's a process going on where I deposit $1,000 in a bank account that returns interest continuously according to an exponential model at 8% per year. How much do I have after 5 years? Well, I would put a 1,000 there. And what did I say, 8%? I would put a 0.08 there. And then I would plug in however many years I want to go by. I would crank out that number, and that's how much money I then have. The example we're going to look at here is a decay problem where a radioactive substance is decaying. This decay follows an exponential function. So we've noted that 112 grams of a substance dropped to 80 after 17 days, and we're being asked to find the decay rate, or the constant K. Going up here and just plugging in T, K, and A0 and cranking out a number is easy, but it's no fun. It's more fun when we're given 3 of the 4 or 4 of the 5 values and we have to discover the other missing piece. So if I take that equation and load it up with this information, that means we started with 80 grams. It was allowed to decay for 17 days. So there's A0 e to the KT, and the resulting amount. Hey, I just did that backwards, didn't I? And you know what? I'm not going to go back and change this video because making mistakes is good. What did I just do here? I accidentally switched these two numbers. A0 is supposed to be the initial amount, the amount I started with, right? 80 isn't the amount I started with. 112 is the amount that I started with. So I need to switch these. Like that. Okay, now I'm going to rewrite the equation so that it's correct. Our job is to discover the decay rate, so we have to solve this expression for K. If we're going to dig our way into K, the first thing that has to go is the 112. Therefore, we will divide both sides by 112. Now, 80 over 112 can be reduced because there's at least a 2 in common among those two numbers. The next thing that has to go, if we're digging our way into K, is the base E, and we eliminate that by the application of the partner logarithm, which is the natural log. So we take the natural log of both sides. And remember that the whole point of doing this operation, applying a natural log to the exponential with e, is that the natural log and the e eliminate each other, and the 17k just drops down on its own. And now we can divide both sides by 17. And again, I'm sticking with the 80 over 112. I should be reducing it. I could probably cancel some 4s, if not something even better. Maybe there's a no, there's not an 8 that's going to go in. So at best, I think I could cancel some 4s and shrink that number down. But yeah, whatever. Here's the decay rate. Now we're going to use the decay rate to determine the half-life. So since I'm going to use it, okay, maybe I will, I'm going to dig my way down. If I have 80 over 112, I can certainly divide out a 2, leaving a 40 and a, oh boy, 56, which tells me I have more canceling to do. How about 1/17 natural log of, let me take out another 2. That would leave me with a 20 on the top. And factoring 2 from 56 will give me 30, 29, 28. Goodness. And then hammering away again. Factoring out another 2. How about 10 over 14? Wow. And how about 5/7? Good grief. So that means there was a 14? No, that doesn't make sense. Anyway, there was something in common between the 80 and the 12 that let me dig this fraction all the way down to natural log of 5/7. And let's see, let's make sure I did that right. Half. Yeah, I think it's okay. And if it's not, send me an email. And then maybe I'll have to redo this page. But we're going to use this decay rate now in its simplified form to determine the half-life of this substance. All right. The half-life of a substance is how long it takes for half of it to decay away. Well, half of what? Well, it doesn't actually matter. We don't need to specify a starting amount because I'm going to build the right-hand side with this particular K. Now, it's gruesome. Right? There's A0 e to the KT, the right-hand side of the exponential process. If I'm investigating half-life, I'm asking a question. Yeah, hey, if I started with this much, how long does it take to decay to half of that? That means starting with this value, I want the resulting value to be 1/2 of that, and then boom, boom, the A0s cancel. So to investigate half-life, I don't need to worry about a starting amount. And now I've got 1/2 equals e to the 1/17 times natural log of 5/2 times t. To solve for t, oh boy, that's up in the exponent, so I need to get rid of e. So I'm going to take the natural log of both sides. I'm going to speed this up a little bit. I'm going to avoid the part where I write the natural log on both sides and then let the natural log do its thing. I'm just going to go right for the throat here. Take the natural log of both sides, let the natural log and the e eliminate each other on the right-hand part. And then I'm going to solve this for t. Now, this is getting a little messy. So here's what I'm going to do. I'm going to take the easy way out. I'm going to show you what it isn't. Okay? If I solve for t, maybe I multiply both sides by 17. Like this. There, I've multiplied both sides by 17. And now I need to divide by natural log of 5/7. So maybe I divide by this, and I get natural log of 7/5 then on the other side, times 17 times natural log of 1/2 equals t. That is incorrect. I'm going to leave it to you to decide what I did wrong and how you should fix it. Ha ha.